Hello everyone. In the last class we started phenols and we saw what are the different ways in which phenols can be prepared either at an industrial level or on a lab scale preparation. From there we talked about the physical properties of phenols and saw that how they are different from alcohols and moved on to studying the reactions of phenols, which were essentially discussed in two ways, either on the basis of the reactions of the nucleus, the phenolic ring, or the hydroxyl group, and we saw what are the similarities and differences the phenolic OH has with the hydroxyl of an alcohol. We discussed a variety of reactions on the nucleus, where we saw that the nucleus is activated by virtue of the hydroxy group, which activates the ortho and para positions, and that is why when we have to carry out reactions like an electrophilic substitution reaction of a phenol, it is a much more active substrate as compared to an unsubstituted benzene. And then we also saw that how different reactions like a halogenation, sulfonation and nitration yields a mixture of ortho and para products, and this mixture can be selectively generated. So, instead of the mixture we can selectively get one isomer, one regioisomer depending upon the conditions we choose for the reaction. That means the reaction can either be kinetically driven or thermodynamically driven, which yields us a particular regioisomer. Today we are going to continue on with this reactions of phenols, and we are going to learn one important reaction which is called the Reamer-Tiemann reaction. So, we are continuing on with the reactions of phenols on the nucleus, and in this the first reaction for today is the Reamer-Tiemann reaction, and in fact this is the third of its kind when we are talking about the reaction. So, in this an important reaction is the Reamer-Tiemann reaction based on the name of these two chemists. So, it is a name reaction, as you can easily guess. The reaction is important because it gives us an access to formilated phenol. So, the reaction enables us to carry out an ortho formylation of phenols. So, a formyl group can be introduced on a phenolic ring with the help of this reaction. So, essentially what the reaction involves is that you take the phenol, take it in a biphasic solvent system. So, the biphasic solvent system comprises of chloroform and an aqueous solution of sodium hydroxide. So, you take NaOH aqueous, and when you do this reaction you usually have to take 3 equivalents of the alkali. When you heat all these constituents at about 70 degrees followed by an acidic workup, you end up with two products, both formilated, and one is ortho-hydroxybenzaldehyde, which is the major product, which we also call as ortho-salicylaldehyde, and the minor product is the para isomer, which you obtain along with formation of NaCl and water. So, this reaction is important because it is giving us an access to the aldehyde substrate on the phenolic ring. It does not require anhydrous condition. So, Reamer-Tiemann reaction, the importance is that the reaction does not require anhydrous conditions for carrying out this formylation. Okay, let us take few more examples to see the kind of products which we obtain if we have another reagent instead of chloroform, like a CCl4. So, you start with a phenol in the same manner, treat it with carbon tetrachloride in the presence of aqueous alkaline solution followed by acidic workup. The product which you get in this case is not the aldehyde, but it is the carboxy derivative, the corresponding acid which you get as the major product. So, in this case you get ortho-hydroxy benzoic acid or salicylic acid as the major product when you carry out the reaction of phenols with carbon tetrachloride instead of chloroform. So, you end up with a mixture again of the ortho and the para isomer, the ortho being the major and the para being the minor. Let us take another example. If you already start with a para substituted phenol like a paracresol and you subject it to Reamer-Teamer reaction conditions, since it is already para substituted, so you would expect the formylation to go at the ortho position, but along with this an unusual product is seen in this case, which is this keto form along with these two substituents at ideally the para position. So, this is an unusual compound with the para substituted phenol which we see. If you take the ortho substituted phenol for that matter, in this case the product which you see, since it is already ortho substituted, so the product mono substituted this side. So, what you get is the para formylation and you get this sweet smelling compound which is called vanillin. Let us look at the mechanism of what is happening in the reaction, what is happening and how chloroform is the reagent and it is giving you a formyl unit. So, what is happening? Let us look at the mechanism. So, the first step is that chloroform under alkaline conditions in the presence of the base, it gives you, it abstracts the proton of chloroform and gives you a carbon ion. So, it gives you this trichlorocarbon ion which again loses a chloride ion to give you this intermediate which is called the dichlorocarbene. So, in this reaction it is this dichlorocarbene which is the active intermediate and the reactive species which is carrying out the formylation. So, once this dichlorocarbene is formed, it has electrophilic character. The next target would be that it would look up for any nucleophilic site. So, what we have in the reaction is the phenol in aqueous alkali, it easily would form the sodium phenoxide ion and in fact it would exist in the form of this phenoxide ion, and the dichlorocarbene which is electrophilic. So, when it happens to exist in the form of the sodium phenoxide, it in fact increases the nucleophilicity at the ortho position. So, the nucleophilicity at the ortho position of a phenoxide is much more as compared to phenol. So, this activated ortho site attacks the carbene which is electrophilic carbene, and what you get as an intermediate is this moiety which under aqueous conditions picks up the proton. So, all these are the transient species which are being generated, and the next key step would be the aromatization. So, the keto trying to change to the enolic form. So, what we get is back the phenoxide ion with the ortho position substituted with CHCl2. Okay. So, in this case there is loss of this proton, and the next step is the hydrolysis. So, once you generate this CHCl2, okay, I will write it again. Once you generate this intermediate here, so the two chlorines on this carbon, right, which are electron withdrawing in nature, okay, they make this carbon partially positive, and under alkaline conditions chloride is lost and replaced by the hydroxide. The substitution takes place twice one more hydroxide unit adds up. So, what you get is right, and the last step is removal of a water molecule. To give you the orthoformyl substituted phenoxide, which under acidic workup gives you the corresponding orthoformylated phenol. So, this is the most plausible mechanism for the Reamer-Teamer reaction resulting in the orthoformylation. So, since you can see that the ortho position is activated and even the para position is activated, right, both are nucleophilic sites. So, the reaction also gives us the para formylated product, but as a minor isomer. Okay. Let us see the unusual case when the reaction was being carried out with the para substituted phenol, that is the cresol. What was happening? So, you have the phenoxide ion of paracresol and you treat it with dichlorocarbene. Okay. Same thing at the ortho site, the reaction occurs the usual way, just what we saw few minutes back. You get this intermediate with the methyl substituent at the para position, and we also see that the other intermediate is possible in which the CCl2 attacks the para position. So, you get this another intermediate. So, you get two of them, and the next step from here would be the ortho substituted would work the same way as we saw above, that in the aqueous conditions this is going to pick up the proton followed by aromatization to give you the phenoxide ion, and this is subsequently subjected to the alkaline hydrolysis and further to the acid catalyzed workup, and it gives you the orthoformyl product. In the other case, when you are getting this intermediate being also generated during the reaction and you carry out under aqueous conditions, when this reaction, what is going to form is this, right. Now, for the reaction to take place, for the next step there has to be a hydrogen here, a proton which has to be lost for it to aromatize, but since no proton is present at the para position, so the reaction stops here and you get this as the product. So, there is no hydrogen which is available for the reaction to proceed the usual way, right, and therefore, it stops here and does not aromatize, giving you this as the side product. Okay, let us see what happens with carbon tetrachloride when we start with. Okay. With CCl4, we said that we are getting the corresponding acid and not the formylated compound. Okay. So, what is happening with CCl4? Again, phenol is forming the phenoxide. Okay. So, this is your nucleophilic site which is created. Now, the chlorines which are -I electron withdrawing create this delta positive charge on the carbon, which is now the electrophilic center, and is attacked by the nucleophilic ortho site to give you this intermediate which rapidly loses the chloride ion and results in the formation of this, which again quickly aromatizes as was seen with addition of dichlorocarbene, it aromatizes and it gives you this compound, which further undergoes hydrolysis under alkaline conditions to give you this intermediate, which rapidly would lose a molecule of water. This is followed by acidic workup, and the salt is converted to phenol along with formation of the installation of this carboxyl group at the ortho position. Okay, so this is how we see that when we have a carbon tetrachloride, we end up with the acid and not the formyl group, and this acid again is important because we can subject this acid to esterification. Okay, so if we treat this with alcohol, acid catalyzed conditions, what we get is this molecule. We carry out the esterification, we get this molecule which is called methyl salicylate or oil of wintergreen. Okay. So, this particular compound has medicinal properties and it is used as a relaxant for muscular pain. Okay. So, this is one way in which we can further derivatize this salicylic acid into methyl salicylate, the ester derivative, and we can also carry out its acetylation with acetic anhydride. When we carry out the acetylation of this compound, the phenolic OH is the one which will get acetylated to give you this acetyl salicylic acid, which is nothing but the pain reliever known by the name aspirin. So, the salicylic acid is an important precursor for these two medicinally active compounds and can be synthesized through the Rearrangement route by using carbon tetrachloride as the reagent. Okay, we move on to the next reaction, which again furnishes the carboxyl group on a phenol, and this reaction is known as the Kolbe's reaction. So, right now it is essentially some of the name reactions which we are dealing with, the Kolbe's reaction or the Kolb-Schmidt reaction. What the reaction involves is you take the phenol and you heat this phenol which exists in the form of phenoxide ion. So, you take the phenol under alkaline conditions, right, and you treat it with carbon dioxide gas, okay, at a high temperature and under pressure. So, of the order of 100 atmosphere. When you heat it and this followed by acidic workup, the product which you get is what you just got above by the Rearrangement reaction, that is the salicylic acid. You get this product also through the Kolbe's Schmidt reaction. When you carry out this at 120 to 140 degrees centigrade, you get this orthoisomer, and if the same thing is carried out at a temperature greater than 140 degrees centigrade, okay, you get the para isomer, you get the para hydroxy benzoic acid as your main product. So, essentially what you can say is that the reaction involves heating of your sodium phenoxide, which will essentially exist under alkaline condition, phenol will exist in this form, and you treat it with CO2 120 to 140 degrees or greater than 140 degrees. What you get is the para isomer, and in this case you get the ortho isomer, and what is happening is that again this is an activated ortho site because it is existing in the form of the phenoxide ion. So, it is reactive. Okay. So, it is the nucleophilic site, and the carbon dioxide, it acts as a weak electrophile. Okay. This is a weak electrophile, and you are having a strong, more reactive nucleophile towards the electrophilic substitution reaction. So, essentially the reaction is an electrophilic substitution reaction, and if you look at the mechanism, it involves under alkaline conditions. You know now by now that the phenol will exist in the form of phenoxide ion, and your carbon dioxide is the electrophile in this particular case. So, as would be expected, it would engage in a electrophilic substitution reaction with the phenoxide ion. And this would lead to a quick tautomerization to give you the keto form changes to your enol form, and I am writing straight away the OH here, and what you get is this molecule, right. So, this is in the form of its sodium salt, and then when you do an acid workup, what you get is the salicylic acid. So, this is the reaction of phenols with carbon dioxide called the Kolb's reaction, again used for the synthesis of orthocarboxyphenols or salicylic acid in this case. Let us look at another type of reaction. So, phenols, as we know, are activated species, and they are quite prone to oxidation. So, already the hydroxyl group bearing the lone pair of electrons make this species highly susceptible to oxidative conditions. So, they have high electron density, and because of this they easily get oxidized. Even in air they will get oxidized on long keeping, and they develop a pink color. Okay. They give a pink color. Even when you keep it in air, it will undergo aerial oxidation. So, what is happening with the phenols, which are a reactive chromophore susceptible to oxidation? So, in the presence of oxygen and light, phenols get oxidized to quinones, okay, and what you get is this kind of a molecule which is called para-benzoquinone. And the para-benzoquinone, again in the presence of more phenol which is there available, it forms this kind of a hydrogen bonded compound which is responsible actually for giving pink color to phenols on long keeping, and this compound is known as phenoquinone. So, this is the molecule which is pink in color, and the pink color which develops in phenol is because of the formation of this molecule. Phenols can also get oxidized by other reagents like the regular reagents which we studied earlier, the chromium based Jones reagent. With the Jones reagent, phenols get oxidized to the corresponding para-benzoquinone. Okay. If you oxidize it with silver oxide, it gets oxidized to the corresponding orthoisomer, orthobenzoquinone. And then there are other oxidants also, the stronger ones, the potassium permanganate, the dichromates, which also carry out the oxidation of phenols and give you the corresponding quinones with different kind of substitution. So, either ortho, para or mixture. Another oxidant which is used for phenols oxidation is potassium persulfate, which in the presence of KOH under alkaline conditions gives you this molecule which is called quinol. So, the conversion of this phenol into quinol. So, you are taking essentially reacting it with alkaline potassium persulfate, and this reaction is known as Elb's persulfate oxidation. Conversion of phenol into quinol, Elb's persulfate oxidation. Okay. Another named reaction for phenols is the Gattermann's aldehyde synthesis. So far you have seen that Reamer-Teamer was one method to get the ortho-formylated phenols. This is another method to get the formylated phenols, and it is known as Gattermann's aldehyde synthesis. In this, what you start with is a phenol. You take the phenol and treat it with a mixture of HCl and HCN, and the conditions are anhydrous in this case. So, that is why I told you in the Reamer-Teamer the good thing was that you do not need anhydrous condition. So, you have to use anhydrous AlCl3, and it gives you an intermediate imine which eventually on the aqueous workup will give you treatment with water, it gives you salicylaldehyde, the orthoformylated phenol. So, if you look at the role of HCl and HCN, they are essentially the providers of the formyl group. So, HCl and HCN together gives an intermediate imine which is a chloroimine, and the phenol, now this is not under alkaline condition. So, the phenol is existing in the form of phenol. Okay. This phenol on reaction with the imine, the chloroimine, the ortho position anyways is activated in a phenol. So, it undergoes this substitution in the presence of the Lewis acid substitution, and you get this intermediate imine attached at the ortho position, and this immediately aromatizes to give you the ortho imine substituted phenol, which on hydrolysis gives you the corresponding formylated phenol. So, this is the Gattermann's aldehyde synthesis, again for synthesizing the formylated phenols at the ortho position. Okay. Another reaction, very important reaction of phenols, is the coupling reaction with diazonium salt. It is a very interesting reaction because you end up seeing a dense colored product which is like a dye, and the dye we call is a azo dye. So, arylamines essentially they form the diazonium salt. Okay. So, the diazonium salt of arylamines through the Sandmeyer's reaction. So, you get the aryl diazonium chloride, and this is treated with, because the reaction is under alkaline condition. So, your phenol is existing in the form of phenoxide. So, when the diazonium salt is treated with the phenoxide ion, what happens is this kind of a coupling reaction takes place under alkaline conditions. Chloride ion is lost from the diazonium, and what you get is N double bond N. So, you get this intermediate, and this intermediate again, as one would expect, would like to aromatize to give the corresponding phenoxide here, which on acidic workup will give you the colored compound, which we call as the azo dye. So, this is a colored compound and this is para hydroxy azobenzene. So, you get these azo dyes which are colored compounds, and they in fact are kind of a way to see that the amine is a primary aryl amine, and it forms the diazonium after diazotization, and then it couples with the phenols. Different kinds of phenols form different types of dyes, right, and you get this molecules. Okay, the next reaction of phenols is called a Thaline reaction. A Thaline reaction is essentially a condensation reaction. So, a condensation means the species, the substrates are reacting with the release of small molecules. So, what are the substrates involved? As the name says, Thaline reaction, and it is a reaction of phenols. So, one substrate is a phenol, which we take 2 moles and we treat it with phthalic anhydride of phthalic acid, and the phthalic anhydride is taken 1 mole, and these two are treated with in presence of a Lewis acid or even concentrated sulfuric acid, and they undergo condensation. That means they are undergoing loss of a molecule which is water in this case, and the product which you get is called phenolphthalein, which is a colorless compound, but it is an important acid base indicator. It is an acid base indicator. It is colorless in acidic conditions and turns to pink under alkaline conditions. So, whenever we carry out titrations, the acid base titrations, we can use phenolphthalein as an indicator. So, the reaction involves 2 molecules of phenols. So, we have 2 phenols and they react with 1 molecule of phthalic anhydride. So, your phthalic anhydride is this in the presence of zinc chloride or aluminum chloride anhydrous. So, the reaction is essentially the condensation with the loss of water molecules. So, one is this para hydrogen para to the hydroxyl, another para to the hydroxyl, and the oxygen. So, this is lost during condensation, and the product which you get is this molecule which is called phenolphthalein. So, in alkaline conditions this gets, it converts in the form of phenoxide ion, and then this opens up and it gives you the pink color. So, this is a reaction of synthesizing phenolphthalein starting from phenols. Another reaction for phenol is the Lieberman's Nitroso reaction. This reaction in fact is used to test phenols. It is a test for phenols because it is a reaction which can be monitored through visual changes. So, it gives you different colors as it proceeds. So, what happens during the reaction is you start with the phenol. If the molecule is a phenol, if the compound in hand is a phenol, you treat it with NaNO2 sulfuric acid. When you treat the phenol with sodium nitrite and concentrated sulfuric acid, you see the development of a transient brownish red color. A transient brownish red color which soon changes to a blue green color, and if you dilute this solution with water, so on dilution with water, the blue green changes to a permanent red color, and now to this red colored solution if you add the base NaOH, it restores the original blue green color. So, these are the different color changes the reaction undergoes, starting from this transient color to a blue green color to a red color and back to a blue green color as you dilute it or you treat it with alkali. So, what is happening? What are the different colors due to and what are the species involved? So, if you look at this reaction and what it is going through, you treat the phenol with NaNO2 H2SO4, which is essentially the nitrous acid, and we have done this before, that it leads to the nitrosation, the electrophilic substitution of phenol. You get the para-nitroso phenol. The para-nitroso phenol can be written in the form of its isomer, which is an oxime, a monooxime. It is a monooxime of parabenzoquinone. So, what happens is that once phenol is converted to nitroso, which is existing in the form of this monooxime, and it sees another molecule of phenol, it forms this intermediate, which is the brown red, the initial brown red color which we see, it forms this intermediate, because the reaction is in the presence of concentrated H2SO4. So, in the presence of sulfuric acid, this brown red intermediate, it changes to the next one, that is the blue green color. So, what happens that it gets protonated in the presence of sulfuric acid, and it forms this kind of a molecule which is the one which gives it the blue green color. So, the initial blue green color and the brown red color, they develop, and now the next is that when you dilute the solution, so you treat it with water, on dilution what you get is the same molecule which you were getting earlier, showing a red brown color. This is the red color. So, you get this molecule which is the indophenol, and this on treatment again with aqueous NaOH, gives you this molecule which is blue in color, and it is also indophenol. existing in the phenoxide ion form. So, you get this change from red to blue, and which is a marker that the molecule is a phenol. So, this is actually a color test for identification of phenols, which is used in the lab. Another reaction of phenols is the use of phenols in the synthesis of resins. So, we have synthesis of the popular phenol formaldehyde resins, which is commonly known by the name bakelite. So, the synthesis of phenol formaldehyde resin, it is again a name reaction, the Lederer-Menassie reaction for the synthesis of bakelite, and the raw materials involved here are, again you take phenol, you treat it with formaldehyde, these are the two components of the resin. So, you have phenol, formaldehyde, both are in excess, okay. You take excess of the two, and in alkaline or acidic conditions, okay, they yield you bakelite. So, first of all, before forming bakelite, they form some compounds which are the methylol derivative. So, you form the monomethylol phenol, right, when 1 mole of this reacts with 1 mole of formaldehyde, and then when this undergoes reaction with another mole of formaldehyde, you get the dimethylol phenol. And these, a mixture of these molecules, when they are further subjected to high temperature and pressure, they result in the formation of bakelite. So, this is what the synthesis involves, that you start with the phenol, treat it with formaldehyde in the presence of alkaline or acidic conditions. So, depending upon the conditions we choose, we get different types of resins. Okay. If you choose alkaline or acidic conditions, you get different resins, but the reaction is possible under both conditions. You can get the methylol, monomethylol derivative. So, CH2OH can either occupy the ortho position or it can occupy the para position. So, you end up with a mixture of the ortho and para monomethylol derivatives, and when they react with another molecule of formaldehyde, so it gives you the dimethylol derivatives. Okay, so, now it could either be both ortho, so you get a 2,6 dimethylol, or it could be ortho para, you would get a 2,4 dimethylol. So, you get a 2,6 or a 2,4 dimethylol derivatives, and now when these are heated, you get bakelite, which is a polymer or a resin which involves different types of cross linking depending upon the monomers which are formed during the reaction and the stoichiometry in which they are generated. So, you get a complex network. The structure of bakelite would again depend, as I was saying, that it would depend upon the ratio of the monomers, the mono and di, which are generated initial step, and the conditions which are being used, the acid or the base for the generation of these monomers, and what you get will be something like this. So, it is a cross linked polymer. Okay. So, you get this kind of extensive cross linking which will depend upon the nature of the monomer. So, you get a cross linked resin. Okay. So, this was about the use of phenols in making phenol formaldehyde resins. Another reaction, important reaction, which is actually not a reaction but a rearrangement reaction, is called Fry's rearrangement. So, Fry's rearrangement is an important reaction of phenols in which the acyl group migrates to the ortho and para position. So, what are we talking about? So, if you recollect, when we talked about the acylation of phenol, so you start with the phenol, okay. This phenol essentially behaves as a bidentate nucleophile. It is a bidentate nucleophile. If you subject it to a Friedel-Crafts acylation, there are two possibilities. It can either undergo a C acylation or it can undergo O acylation. So, depending upon the conditions you choose. If you carry out the acylation, let us say with acetyl chloride in the presence of AlCl3, you get C acylation, which is a thermodynamic controlled product, and you carry out the reaction with acid chloride, you get the O acylation product, which is a kinetically controlled product. So, essentially what is happening that in Friedel-Crafts acylation of phenols, when you carried out an O acylation and converted the phenol into this ester, the phenolic ester, okay, this is phenyl acetate, converted this to phenolic ester. In the presence of AlCl3, okay, in the presence of AlCl3 as the catalyst, this ester can undergo a rearrangement to give you this product, which is hydroxy aromatic ketone. So, you get this para hydroxy acetophenone. So, when you carry out this reaction with AlCl3 as the catalyst, it involves migration of this acyl group at the para position when the reaction is carried out at 25 degrees centigrade. So, you get these hydroxy aromatic ketone, and if you take this para hydroxy acetophenone or the hydroxy ketone at the para position and you further subject it to AlCl3 catalytic treatment at a high temperature 160 degrees centigrade, in that case the product changes to the more stable orthoisomer. You get the more stable orthoisomer, which is a thermodynamic product. So, what we are seeing here is that this Fry's rearrangement can give us selectivity in terms of the ortho or the para isomer. So, the para isomer is a kinetic product at low temperature is generated, and if the same is heated, it converts into the more stable, thermodynamically stable orthoisomer. And if we start from phenyl acetate and directly subject it to AlCl3 treatment at 160 degrees centigrade, it gives us the more stable orthoisomer in those conditions. So, if you carry out the reaction at any temperature in between the two, you will end up with a mixture of ortho and para products, and the ortho and para mixture if you get, then they need to be separated with the help of steam distillation. So, steam distillation, because the orthoisomer will be volatile. So, if you see that in case of orthoisomer, if you just look at the structure, it would be an intramolecular hydrogen bonding which is stabilizing the orthoisomer, and therefore, it will not undergo intermolecular hydrogen bonding which keeps it as a volatile liquid, and it can be separated from the corresponding para isomer with the help of steam distillation. So, it has its volatility with steam is what helps us to separate the two isomers. if you have this molecule. So, if you have this molecule and you treat it with AlCl3 again at 25 degrees centigrade, low temperature, kinetic control, you expect to get the para isomer exclusively, and if you do this at 165 degrees centigrade, you get the thermodynamic product, the orthoisomer exclusively. And if you again treat this with AlCl3 at a high temperature, the para isomer changes to ortho, and in between 25 and 165 we get a mixture of ortho and para products. So, this is what the rearrangement involves, that there is a migration of this acyl group from oxygen to carbon, which could be ortho or para under different conditions. So, what is happening and what is the role of AlCl3 in this case? So, when you start with your ester, the role of AlCl3 is that it forms a complex with the starting material and activates it. So, essentially its role is to activate the starting ester. Okay, so it forms a complex with the ester and activates it okay. So, if I show it like this, this is a positive charge, right, and then so it forms this activated complex which undergoes dissociation. So, it dissociates, and when it dissociates, it gives you this intermediate, right. So, this dissociates to give you this intermediate, which subsequently furnishes this acyl group, right, which can again be written in the other resonant form. So, you get this species, and now what happens, that what is left out there is this oxygen AlCl3, right, and what phenol does, it is activated phenol now, okay. So, it attacks your carbon with this positive charge, okay. So, it will attack here. So, if I have to just show, this is going to attack this carbon, and what you get is this intermediate, which would undergo aromatization to give this product, which is still the activated OAlCl3 linkage, which on hydrolysis gives you this orthoacylated phenol. So, this is the proposed mechanism for Fry's rearrangement with the help of AlCl3 as an activator of the starting material and the product. So, with this we come to an end of the discussion on phenols. What we have covered is quite extensive, and next time we are going to start the remaining part of this module, which is ethers. So, till then, bye.